Power functions with negative integer exponent, investigation 1. In this investigation, we will study the properties of functions of the form y equals x to the power of minus n, where n is a positive integer. Okay, so let me write this function formula here. Function in a form y equals x to the power of negative n. Now, you know already that since n is a positive integer, then if you place minus sign in front of it, you get a negative integer. And this whole thing here, this minus n here, is called the exponent, and therefore we are talking about the power function with negative exponent. From your prior studies in mathematics, you should be able to rewrite it using this formula. This is 1 over x to the power of n. This is the most essential part of, that you will need to understand that this is actually so. Okay, so that x to the power of n is 1 over x to the power of negative n or minus n equals 1 over x to the power of n. Just a short try to explain it. You know that x to the power of negative n can be understood or rewritten as x to the power of 0 minus n. And now, using the well-known formula, this can be written as x to the power of 0 divided by x to the power of n, where you know already that x to the power of 0 has to be 1. So this is 1 over x to the power of n, and this is in line with what I have just said a sec ago. So this is the defining thing here, and we will use it in what follows. Okay, so we are studying now the functions in a form y equals 1 over x to the power of n, or you may understand them as x to the power of negative n. Now, in part A, use GeoGebra Graphing Calculator app to draw graphs of 6 power functions, and here they are. F sub 1 y equals x to the power of minus 1, then we have f sub 2 x to the power of minus 2, and so on until f sub 6 y equals x to the power of negative 6. Okay, so we will use the prepared interactive model. You can prepare it yourself, or you can just click here and get what I have here. Okay, so here are the graphs, all of them, and perhaps I will just hide them all and start first by those which have the odd negative power. So first one is x to the power of minus 1 or negative 1. So this is a well-known function, y equals 1 over x. You know, this is the reciprocal function. It passes through these 2 points, as should be already obvious from your prior studies. Now you may add the function x to the power of negative 3, and you see it's very similar. It exists in the first and the third quadrant in the same way as the function f sub 1 existed, and passes through the same 2 points, but behaves somewhat differently. You see that in this region between 0 and 1 it is somewhat steeper than before, and now here in this region from 1 to infinity it tends or flattens away towards the x-axis, and the same goes also here. In this region the function is more steep, and in the region from negative 1 to negative infinity actually this is more flattened. Now let me add f sub 5. So you see f sub 5 is of very similar form, but even more steep here and even more flat in this region to the right, and so also for this third quadrant. So these are the functions with negative odd integer exponent. Now let me remove them and try the functions with negative integer exponent, which is even. So here we are, this is the function y equals x to the power of -2, and you see that the graph exists in the first and the second quadrant, passing through these two important points, and you see its behavior there. Okay, now if I add x to the power of -4, this is it. So again, it's more steep in this region around 0, between -1 and 1, and it tends to the 0 value as x tends to infinity, and is more flattened, like you can see, in the region from 1 upwards or from -1 downwards. Okay, and now the function f sub 6, x to the power of -6, it's a very similar but even more steep here and even more flattened there. Okay, so here they are, all 6 of them. You see them all at once. Okay, so in part A we had to draw them, and this is what we did. We observed what we got, and now let us move on to some understanding. So in part B we should explain why all the graphs pass through the point 1, 1. So you saw it, all of them passed through this point. Now to explain this, all we have to do is to show that for any of those functions, f of 1 should be equal to 1. Only then the point 1, 1 lies on the graph. You may understand that the first coordinate is the x and the second coordinate is the y coordinate. So only then the point lies on the graph when if you substitute x for the value here and you evaluate f of 1, you get 1. So is it so? Let us see. Y is 1 divided by x to the power of n. So this is the general form of the function, and now you should check that when you substitute 1 for x, like this, you should get 1. Okay, is it so? 1 to the power of n, when n is a positive integer, is always 1, so you have 1 over 1, and this is really 1. So we were successful in proving that all those functions must pass through the point with coordinates 1, 1. This was the part B. Okay, let's move on to part C. In part C, explain why the graphs of all power functions with an odd integer exponent pass through the point with coordinates -1 and -1. Okay, so imagine that n is odd. N is odd. So maybe, for example, n equals either 1, 3, or 5 in our case, and it can assume all the other odd values, of course. Now we have to show that the point with coordinates -1 and -1 is the point through which the function's graph passes. Oh, okay, there should be -1 here. Okay, so to prove that, we have to show that since this is x and this is y, we have to show that the function value of the function in -1, so f of -1, that it equals -1. To do that, let us write down the formula of the function y equals 1 over x to the power of n, and you see it's 1 over -1 to the power of n. And since n is odd, then you can see that -1 to the odd power raised to the odd power is just -1, so it's 1 over -1, and it must be -1. So really it is true that f of -1 is -1, and therefore this proves the fact that all those graphs with the negative odd exponent pass through this point. Okay, now in part D we have to show similar thing, that all the graphs of those power functions with an even integer exponent pass through the point with coordinates -1 and 1. Okay, so let me draw a line here and let's do part, it is part D. So in part D we are asked to show that in a situation then when n is even, so for example n equals 2, 4, 6, etc., that in this situation the function values pass through the point with coordinates -1 and 1. To show that, it suffices to prove that function value f of -1 equals 1 in such a case. Okay, so let us do that. Function value f of -1, according to the formula describing the function, is 1 over -1 to the power of n. Since n is even and you raise -1 to an even power, you should get 1 over +1, because -1 raised to the even power is just 1, so therefore the answer is 1. Okay, so we were successful in proving that f of -1 is 1, and therefore this point with x coordinate -1 and y coordinate 1 has to be the point of the graph of the function. This point lies on the function, so it is in a function. Therefore this is the proof. This is all that we needed to do. Okay, this was part D. Now let's do the following part. Explain why the line x equals 0 is the vertical asymptote for all the graphs, and why y equals 0 is their horizontal asymptote. So here we are again, the concept of asymptotes. Let us look back at those graphs. So you see that all of them tend to either positive infinity or negative infinity as x tends to 0 from the right, or as x tends to 0 from the left. Okay, you see that they increase or decrease like that and approach this vertical axis. So the vertical axis should be the asymptote. To explain why this is the asymptote, well, it means to show that the function is not defined there. Okay, so is it defined? Well, since the formula for the function is y equals 1 over x to the power of n, you know that you run into trouble if you try to substitute 0 for x. So if you take 0, so if you take x equals 0 and substitute here, it's not defined. Therefore, in line with what we know already from the prior studies, this place, x equals 0, should be a place where the vertical asymptote exists. Okay, so this really must be a vertical asymptote. Now, as for the second part of the exercise, where we are asked to show that y equals 0 is the horizontal asymptote, so let us check it. Is it so? This line here, this line, is the horizontal line y equals 0. And you see that really all the branches of the graph approach this line as x tends to infinity, and also they approach it either from above or from below as x tends to negative infinity. So really it seems that the line y equals 0 is a horizontal asymptote. The question is, do they ever cross this line? Does any branch of these graphs cross this line? And my answer is definitely no. And the reason for this fact is this. Imagine that the function y, you know that this is 1 over x to the power of n, and imagine that it would cross the horizontal line y equals 0. Then, of course, this would be 0. So imagine that you would have the equation 0 equals 1 over x to the power of n. Now, this means that if you multiply times x to the power of n, it means that 0 equals 1, okay? And this is a nonsense. This is a piece of nonsense. This never happens. 0 is not 1. So if any branch of those graphs crossed its horizontal asymptote, it would amount to asking that 0 equals 1, and this is not possible. Therefore, they never cross these lines, these graphs never cross the horizontal asymptote. As for the vertical asymptote, it cannot be crossed either, and the reason for that, if any graph crossed the vertical asymptote x equals 0, it would mean that the point of the graph would have the x coordinate equal to 0, but you cannot have the point with x coordinate equal to 0 because the graph is not defined for such value. So this would be another piece of nonsense. So it's not true. It would not be true. Okay, now for the last part. In part F, we are asked to play with this dynamic interactive model of power functions prepared in GeoGebra Graphing Calculator and explain why as the power increases, the graphs become steeper near the origin and flatten away from the origin. Okay, so here it is, this new model that I want you to study. There is one slider in it, and you may change it. So this slider represents n in the formula x to the power of minus n. Now the slider has the value of 1. You see the graph passes as it should through these 2 points. So as the n is, in this case, it is odd, it should pass through these 2 points. And when I increase it to number 2, to the value of 2, the graph changes and passes through these 2 points, and then I can increase it even further to value 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. And you see what happens, that really the graph tends to be steeper in the region between 0 and 1 and between -1 and 0, and tends to flatten in the region between 1 and infinity, and between the region from -infinity and -1. So you may see it. Now let me move back to the original value. Okay, so I can use this way to change it. Okay, now we should try to explain why this happens, why this behavior. So imagine that you take the function value x equals 0.5, and we have to explain why this moves upwards. This point here with coordinates 0.5 and 2 moves upwards when n increases from number 1 to number 2. Okay, so let us see. Imagine that we have the function y equals 1 over x to whatever power. Well, okay, let it be the power of n, and take the function at x equals 0.5. Okay, so for this value, it is actually 1 over 0.5 to the power of n. And it means that it's 1 over 0.5 times 1 over 0.5, sorry for that, times etc. times 1 over 0.5. You may know that 1 over 0.5 is 2, so we have 2 times 2 times 2, etc. times 2. So the greater the value of n, the more factors of the value of 2 are there in the expression evaluating y. So when n is just 1, you get the function value of 2, which corresponds to this. At 0.5 we have the function value of 2. Now if we change the slider to position 2, so when n is 2, then instead of just 1 2, you get 2 2's. So you multiply 2 times 2, you get 4. So it's a greater value. You can see it that at 0.5 you get the value of 4. So therefore, as n increases, also this value increases, and hence the graph should become steeper in this region. It's very similar in the region between 1 and infinity. take the value of 2. If I take x equal 2, you see that for n equal 1, x equals 2, and for n equal 1, you see that the function value is 0.5. So what I say is this. If I take x equals 2, then the function value y equals 1 over x to the power of n should be 1 over 2 to the power of n, which is 1 over 2 times 1 over 2 times etc. times 1 over 2. All that happens n times, of course, times. So you see each of those factors here has the value of 0.5. So you multiply 0.5 by itself n times 0.5 like this. So what happens is that as you increase n, the result of this calculation must decrease, because it's always 50% of the previous value as you add the following and following factor. So for example, when n is 1, you get just 0.5. Okay, you see when take x equal to 2, you get 0.5. Now, if I increase the slider to the value of 2, at 2 you get the value 0.25. So this one is less, and the reason for that, there are two factors, this one and this one. So if you multiply, you get a smaller answer. So this should explain the behavior of these graphs and should be understood as a sufficient explanation.